All right, welcome to the IARS Virtual Education webinar. Our topic today is artificial intelligence and machine learning to predict intensive care indices and outcomes. This webinar has received no commercial support. The IARS supports anesthesia research and education with the overarching goal of improving patient care. This is the organization's mission and vision. IARS offers many benefits to its members, including monthly issues of Anesthesia and Analgesia, access to the online member community, and discounted registration rates for the annual meeting. To join or renew, visit iars.org/membership. IARS provides free resources for the global anesthesia community. Free IARS membership is available for fellows, residents, medical students, and others in training. Visit iars.org/membership to join. The IARS Membership Committee seeks your feedback on how IARS can provide you with the most meaningful engagement experience. Scan the QR code to take the survey for a chance to win 1 free annual membership or 1 free annual meeting registration. Save the date. Join us May 17th through 19th in Seattle, Washington for the 2024 annual meeting presented by IARS and SOCA. If you missed the 2023 annual meeting, on-demand recordings are available for IARS members. Visit our website for information. After this webinar, join the speakers in the IARS Doc Matter community to continue this conversation. Upcoming webinars, visit iars.org/cme-webinars to register. The next are on June 11th and July 9th. For this webinar, please submit questions via the Q&A button below, and we will get to those at the end of the segment as time permits. Today, we have a great topic. We have 4 speakers, and we can't wait to get going. Our first speaker is, let me introduce him, Dr. Ryan Melvin. Dr. Ryan Melvin, as you pull up your slides to share, Dr. Ryan Melvin is the principal data scientist and endowed scholar at the University of Alabama at Birmingham's Department of Anesthesiology and Perioperative Medicine. His contributions to AI research, including algorithms currently used by government organizations, have been featured in esteemed journals such as the Proceedings of the National Academy of Science and Physiologic Reviews. Leading a dynamic team at UAB, Dr. Melvin has pioneered the development of multiple generative AI tools, ensuring their safety and security for use in clinical research.
Awesome, thank you, Andrew. And I trust my slides are showing as expected, and I will get started.
Looks good.
So I want to talk about fact versus myth about artificial intelligence and machine learning in the ICU and OR. Some of these are a little bit straw man argument, but they're done to make a point. So first off, despite my best efforts, I unfortunately have no financial relationships with commercial interests to disclose. Also, I'm not going to talk about any off-label or drug use at all. I think there is a bit of a myth that AI is a new thing and it's some sort of well-defined technology that's simulating the human brain. And that's not really true, depending on how you want to think about it. AI has existed since about the 1950s in a computational form. And some of the ways folks define it, flowcharts on the walls are AI. They've been around for a long time. The real fact is that AI is a marketing term. In fact, I would argue that maybe we should stop clarifying that means artificial intelligence. I think at some point it just started to mean computer stuff. But overall, you could better think of it as a collection of tools. So there are many tools in the toolbox, just like a tool shed, that we can grab to use. It's not this monolithic thing. It's not HAL 9000. It's not even one type of product. It's many types of products, including things like generative AI, which have taken the world by storm since about December 2022, when OpenAI released ChatGPT as a commercial product. Another myth that I think is really important to dispel is that AI is somehow a replacement for or better than traditional statistical methods. And this is very much not true. In fact, they serve completely different purposes and answer completely different types of questions. So on the left side of the slide, I've got some key points on what it is that statistics does in the traditional sense. It detects relationships, quantifies the significance of those relationships, and you develop hypotheses first. So your hypothesis is a priori, and then you test your hypothesis with statistics. Data science, on the other hand, is about making predictions. A successful machine learning AI data science project makes a really good prediction. It sacrifices often interpretability for getting predictive accuracy, and your hypotheses come last. So you might build a really good model that predicts hypotension, for example. And then afterward, you ask, well, what went into the model that maybe made its predictions really good? And out of that analysis, you might develop some hypotheses that you can then test with statistics. So to sort of summarize that point, in statistics, you form a hypothesis about how features are connected, then test it, and then maybe you use it to predict the future. For AI, machine learning, and data science, it's pretty much the exact opposite order. You build a model that's really good at predicting the future. Then you figure out how the features you used in your model influence those predictions. And then you might form a hypothesis that you can go back and test. These two fields accomplish very different goals. They do have some overlap in their mathematics and underlying tools. But at its core, statistics helps us build and test theoretical models of the world that help us understand natural phenomena. So it really is old school scientific method. I'm going to develop some theoretical model. I'm going to form a hypothesis about a specific event, and then I can go test my hypothesis, and then that gives me weak evidence for or against my theoretical model. And then I do that a bunch of times until it's strong evidence, and now I publish my theory and release it to the world. AI, on the other hand, is about simulating natural phenomena or predicting the outcomes of natural phenomena without regard to an underlying theoretical model. And in fact, if you were to try to parse out what very complicated AIs do, like image recognition or generative AI that's making pictures like the one on the right, or ones that are generating new bodies of text like ChatGPT, the mathematics that are going on, the functions that it generates to make those predictions, would make no sense to a human mind. They are nonlinear models with sometimes billions of parameters, and it's just not a thing we could hold in our head or use to form a theoretical model of the universe. And so they're very different things. One's just about predictions, and one's about like a deep understanding and developing theoretical models. I think an important myth to dispel is that AI might eliminate the need for human monitoring, such as in an ICU. That's very much not true. At least for the foreseeable future, maybe forever, we're going to be using AI tools to augment human monitoring. And I think there are two key things to point out. One, an AI does not care if it gets the answer right or wrong. It has no ethical encumbrance. It won't feel bad if it leads to someone being impaired or dying. And an AI is not going to get sued for malpractice. Its life will not be ruined by a mistake in a prediction it makes. But those are things that can happen to people. And so what we are going to do, and what we should really try to do, is to use AI to augment humans in a way that will maximize benefit and minimize loss. So let me tell you a little story that I think illustrates this really well. The last two cars that I've owned have blind spot monitoring technology. And so if someone is right beside me, a little orange light lights up on my side view mirror. And if I turn my blinker on while someone's right beside me, that orange light will start to blink. Well, there is a way that I could use that signal that will maximize benefit and minimize loss. For example, if I just blindly trusted that blinking orange light and said, well, the light's not blinking, I can change lanes, it's entirely possible that something has gone wrong, that the sensor is blocked or an error has occurred, and someone's in the lane next to me, and I try to change lanes and I hit them. Well, now I'm going to have a very bad day. Or I could always ignore the blinking orange light and say, no, it's blinking, but I don't think there's anybody there. I'll go ahead and change lanes, or I'll go ahead and merge. In both of those ways, I'm not maximizing the benefit and I'm not minimizing the loss. What I could do instead is say, well, whenever the orange light blinks, I'll just check a second time whether someone is next to me. So I'll do my normal, check my blind spot. And if the orange light is blinking, I'll take the couple of seconds to look again. Because in that case, if one of us is wrong, it's not really going to hurt anything because we've had that second check. But if the AI was correct and there's a car next to me, then I have maximized the benefit by not hitting anyone by using the technology in that way. So I think whenever a new AI technology is available in critical care and the ORs, it's incumbent upon all of the users to think through, how do I maximize the benefit of this AI so that when it's right, I can really make a difference. But when it's wrong, we really don't have that much loss happen as a result of its being wrong. Another reason that I think we need to be careful in these automation or in these augmentation senses is there's this phenomenon called automation bias that humans have. If a machine tells us an answer, we're more likely to believe it than if a human told us the answer. That's sometimes why at the checkout lane, when you know that the eggs didn't cost $100, it's kind of hard to argue because they're like, well, the computer told me. That's automation bias. We believe the answer because it came from a machine, although there's no a priori reason to think that the machine is going to be more correct than a human. An example of this will actually come shortly. Andrew Barker is going to present on the topic of how we've tried to maximize benefit with unplanned care escalations. So I'll save that for him. And then sort of wrapping up, I think there's this other myth that combined with robotics, we're worried that AI will eliminate human providers in the OR, sort of like the emergency medical hologram in Star Trek Voyager. They pop up and treat the patient, no humans involved. But for the foreseeable future, we're just not going to be there, maybe beyond our lifetimes. But to sort of cover why that is, I'll briefly do like a 1-minute walkthrough of some of the strengths, weaknesses, opportunities, and threats of these things to let you know where they're at and why this is not a thing that will be happening in the foreseeable future. So AI is, in general, very efficient, very scalable, and generative AI in particular, like image generators and text generators, are surprisingly versatile. They work across a wide variety of tasks. And in a sense, they're continuously learning because they're always getting retrained. But that high efficiency, I can have a conversation with one person at a time. But ChatGPT, for example, is having conversations with millions of people right this moment. Or I could look at one patient's chart at a time, and the AI Andrew will describe can look at many patients' chart at one time and make suggestions. Weaknesses, though, the data in, if it's garbage, then the outputs are going to be garbage. So data quality becomes really important, especially when you're trying to make predictions for patients. If you just have a model built at one center, for example, then your predictions might be really good for that center, but not for other places. Additionally, AI is often hard to interpret, as I described earlier. Very large models, we can't hold what they're doing in our head and have any chance of understanding them. There are some opportunities, I think, especially in telemedicine. I recently did a quote urgent care visit where I just filled out like a 50-question form, and then a CRNP wrote a prescription for me. Imagine if a generative AI took a first pass at saying, well, I think this patient needs this because this is what's going on with them. And then a provider just sort of double checked it. I think there's some opportunities there for high efficiency. And then Many of the large models, generative AI in particular, are owned and controlled by mega corporations, and they're so computationally intensive that we have to send our data to these mega corporations in order to use them. And so I think there's a big privacy and security concern. Also, generative AIs are not FDA cleared devices. At any moment, the FDA could just say, no, we're not going to allow this type of technology, and the story could be over. But also, as a connection to automation bias, if we engage in that automation bias, we can become over-reliant and forget to check what the AI is doing. As an example of something we've tried to do that will help, but not encourage over-reliance, we are monitoring waveform signals in some of our cardiovascular ORs. And out of those, we're making predictions on what the optimal blood pressure for a patient is. So for example, I have 2 patients here, and the lowest their blood pressure could get and still sort of have their brain be correctly perfused is displayed there on the chart with lower limit of autoregulation. Another preview of, I think, a topic that's going to be discussed later in the webinar. And I'll close, this is my last slide, with what I think really is a description of what the future looks like. Machines are not going to replace physicians, but physicians using AI will soon replace those not using it. And thank you all. I think I'll hand it back to Andrew for the next introduction.
Let me get my screen to work here. Here we go. Thanks, Ryan. I really appreciate that talk. That's a great, great introduction to our program today. I'll be giving the next talk. I am the moderator of this, and the next speaker. I am Andrew Barker. Let me try and pull up my slide, share my slideshow here. I am an associate professor in anesthesiology and critical care medicine at the University of Alabama in Birmingham. I am the co-medical director of the surgical intensive care unit and the critical care medicine fellowship director. I have some research interests in ICU delirium, machine learning, and medical decision tools, outcomes research, and implementation science. Let me get my screen shared here. There we go. How's that looking?
Looks good.
Okay, so I want to talk about predicting unplanned care escalations after PACU discharge. I do not have any financial relationships to disclose, and I'm not discussing any off-label or investigational use in this. So when we look at quality metrics, we often talk about ICU readmissions, post-surgical ICU admissions, unplanned, and then all comers in ICU admissions, from hospital admissions, from the ED, and other metrics. It's hard to nail these down as far as incidents. They're based on hospital systems, patient populations, and they're all a little bit different. But in the literature, if you look at ICU readmissions alone, the incidence is generally somewhere between 2 and 10%. If you look at post-surgical unplanned ICU admissions, depending on the patient population location, they can be less than 1% is reported, and as high as 4.9% or even higher. And these risk factors associated with these unplanned post-op ICU admissions are typically cardiac and pulmonary risk factors or perioperative risk factors associated. These outcomes of unplanned ICU admissions and readmissions increase length of stay, cost, and mortality. If we look at the post-op ICU admission planning, we're typically able to plan a patient in the perioperative environment that goes to the ICU. And this is often based on the procedure and its technicalities, the patient, local resources of the institution, and acuity. But when post-op patients do not go to the ICU and they go somewhere else, how do we identify risk for clinical complications in that cohort? So at our institution at University of Alabama in Birmingham, we're a high volume tertiary institution. We see about 40 to 50,000 cases per year on average, a little bit more than that as of late, roughly about 160 cases per day. We have a lot of information to sift through. And it was our interest to see what our post-PACU unplanned care escalations were. And I sort of think of this as essentially a PACU bounce back rate, or readmission rate. The problem is they don't come back to PACU. So a lot of this data is hard to chase down. But what we wanted to define this, here's a definition that we were looking at, is when a patient has surgery, they're discharged from PACU, they go to the inpatient floor or the intermediate care or step down, with whatever terminology you use at your institution. If they're transferred to a higher level of care within 72 hours, those are the patients we were interested in looking at. And transfer to a higher level of care means if they go to the floor and then they're stepped up to intermediate care, or they're on intermediate care, they go to the ICU or floor to ICU. That's what we're talking about. In addition, we looked at our patients that fit this criteria that also had a medical emergency team evaluation and intervention at that point. And what we saw using this definition was our incidence of issues within 3 days is about 5.2% incidence. If you told me my surgical ICU readmission rate was 5.2%, I'd say we probably have something to work on here. Let's kind of drill down on that, because I think identifying these patients at risk for later deterioration, clinical deterioration, would be helpful to know how they can benefit from preemptive care, longer observation periods, alternate disposition plans, and overall better resource allocation. And I think at an institution like ours, that's helpful to look at maybe a more unique way to look at that. We looked at a potential role for machine learning to help us make the decision and analyze the risk. Because we have high operational capacity, we often have a fair amount of, at this moment, PACU overflow volume, where we're holding patients in PACU because our hospital is at capacity. So that influences our PACU workflow. And we have high volume operative throughput in our PACU space. So our big question is there a role for machine learning to help us with the decision making of identifying these patients? And if you're looking at a 5.2% incidence, on average, you're looking at about 2 patients per day that you could help reallocate resources better for. So what we did, we trained a supervised machine learning model to detect differences in patients who had unplanned care escalations within those 3 days of PACU discharge between those who did not. And so we looked at retrospective data at our single center between January 2016 and December 2019. We started off with roughly 138,000 patients, and we excluded patients that were outpatient, cardiac patients. We're looking at non-cardiac patients, but all surgery patients, elective cases, and emergent non-cardiac. We allocated roughly 58,900 patients. And so we had 47,000 patients that went to the training arm of this machine learning, and then roughly about 12,000 patients that went to the testing arm on this. There were no difference between the training and testing data set as far as demographics go. Using our training data, the model was able to predict unplanned care escalation risk with a reasonable level of precision, having an area under the curve of 0.75. That's figure A here on the left. And after the model had learned, using 80% of the patients in the study, it was applied to a test group of patients, and that achieved an area under the curve of about 0.75 equivalently. So pretty reasonable prediction risk, or risk of prediction with that model. So after we did the model training, we examined how the model predicted risk for each patient characteristic or clinical parameter of interest. And for each data point, the model created bins for continuous variables and assigned risk with points for each bin. And the model applies the appropriate risk accordingly. So in this, if you look at this table on the bottom here, we have the last oxygen saturation before PACU discharge. It appropriately assigns risk to low oxygen saturations. If you look in the middle there, maximum heart rate in the PACU stay within the last hour, it appropriately assigns risk to high heart rate and low heart rate. So clinically, it's understanding what we do clinically and not creating a lot of surprises here. Now, the other variable on this table, and this is just an example of the variables we looked at and that the algorithm came up with as far as risk, is non-surgical anesthesia time, which I'll talk about here in the next slide, or in a couple slides. So we next sought to understand the variables that had the greatest effect on patient, on the unplanned escalation of care. And depicted here were the 10 most influential variables for patients whose estimated probability of escalation was greater than 20%. So for each patient, their path is visualized by one of the lines on that chart. This is a Shapley chart, Shapley graph. And moving from lower risk is in the left-hand side to higher risk is in the upper right-hand side. And as the variables increase from bottom to top on the left-hand column, increases in importance. So as a curve bends to the right, with each variable ascending, confers more risk. And so these are AKI, heart rate, respiratory rate, emergency presence, emergency surgery, yes or no, heart line presence, Aldrete score, platelet number, and then blood pressure. So our machine algorithm was able to identify specific risk factors for unplanned care escalations, and some of these risk factors are not clinically surprising, which I think speaks to some of the validity of this model, right? So pre-op AKI, elevated heart rate, respiratory rate, ASA status should not be very surprising, and more importantly, like the machine learning algorithm places rank up to this importance. that agrees clinically, right? Interestingly, this variable called non-surgical anesthesia time was a little bit of a surprise. Something like anesthesia to surgery start time and surgery to finished anesthesia end time may actually be a surrogate for surgical case complexity and process variables. And then missing data was a risk factor, and that may be a reflection of PACU workflow and other practice management processes. So there's a potential for this machine learning risk predictive model to impact a busy PACU workflow, a busy anesthesia day, especially with the throughput that we have in an institution like this. We see that a decision tool could potentially help with targeted evaluation and then subsequent patient resource allocation. And like Ryan was saying, just, hey, the light's blinking, let's look over our shoulder and double check on this. And then there's benefits of machine learning and augmenting this clinical decision making in real time potentially. So future studies are needed to investigate. A prospective use of this model would be very, very interesting and helpful. Testing against an external cohort would definitely give this model some external validity. And there's the possibilities of incorporating this into maybe a newer scoring system or augmenting scoring systems that we have already for PACU discharge that relates to disposition planning, not just necessarily appropriateness for discharge in general. And then potentially impact for process implementation, essentially to reduce this missingness, I think is sort of a fruitful opportunity. So machine learning algorithms can help predict patients at increased risk for unplanned care escalations in this scenario. There's an importance of further studies to validate these findings. And then we see some positive implications for some precision medicine and decision-making tools here to better take care of our patients. And with that, I will move on to our next. Let's see. Dr. Wasson is our next speaker. While you get your slides going, I'll introduce you here. Dr. Wasson is a neurointensivist and anesthesiologist at the University of Alabama at Birmingham. She splits her time between the neuro ICU and the neuro ORs. She completed residency training in San Antonio and a fellowship here in critical care at UAB. And she has an interest in perioperative blood pressure management and cerebral autoregulation. So we look forward to her talk. Thank you.
All right, are my slides showing up?
Yeah, they are.
Okay, great. All right, so he said, my name is Emily Wasson, and I'm going to talk about, this is kind of a forward-thinking, where are we going next with some of this technology? It's a project in the works. All right. I don't have any financial relationships, and I just wanted to mention that the TCD robot technology that I'm going to be talking about, it's not been previously described being used exactly how we're using it, but all the techniques and data collection underpinning the project has been used previously. So as just kind of a background of what I'm going to talk about, I wanted to start with a bit of a background in autoregulation and kind of what we're planning on doing and why. And kind of all goes back to this historical understanding of cerebral autoregulation. And as recently as when I was a resident, I was taught this, this concept that there is this range of blood pressures, typically 50 to 150 MAP, where there is essentially no change in cerebral blood flow through a combination of either vasoconstriction or vasodilation. The brain is able to have this very constant amount of blood flow. And that was kind of adapted when we started to have chronic hypertension as a very common thing that we were encountering. And then the idea was that the curve itself is still the same, and it has this period of flat cerebral blood flow, but it's right shifted because people are chronically hypertensive and they're used to a higher blood pressure. And so when I started to kind of dig around as to where this came from, it actually came from this hand-drawn figure from a review on cerebral blood flow in 1959 by Wasson. And this is actually a collection of data points. Each of these points in here is the mean value of a particular study on various populations. On the left side, you have patients that were drug-induced hypotension. There are some that are healthy young men. There's some that are healthy pregnant women that had malignant blood pressure, drug-induced hypertension. And so each of these data points represents a small study. All of this entirely is less than 400 patients. And each one of these values is a mean blood pressure of a group of people. And so I don't know that this was necessarily intended to show that this is something that's true for every person, but it just kind of got adopted and became widespread in our kind of common knowledge lexicon. And so in recent years, we have started to be a bit more nuanced in thinking about cerebral autoregulation. I have a couple examples of some of the work that's been done more recently. This is a figure from a study by Rosenblatt et al., who looked at septic patients, and they used cerebral oximetry as a surrogate for cerebral blood flow. And then they correlated that in time to MAP, and basically found that there isn't this big period of flat cerebral blood flow with no association whatsoever with the blood pressure. It's more of a like gentle curve with a period that is a little bit that is much flatter and gets close to zero, but never actually equals zero for any long period of time. But the theory still remains that cerebral autoregulation is an important function of our brain's vasculature. And so using these surrogates of cerebral blood flow and mean arterial blood pressure, you're able to find the point at which the curve of that line most closely approximates 0, and the cerebral autoregulation is the most effective at that point. And so this is a graph from that study where they were finding that point and measuring it by time. This is another study by Zeiler et al., where they were looking at TBI patients. They used pulse reactivity index, which is a correlation between mean arterial pressure and changes in ICP. And they basically, the same sort of idea that they're using that as a surrogate for where the cerebral autoregulation is most intact, when those two have the least to do with each other. And so these are some of the data points that they use to come to those values. And then kind of in a more clinical extrapolation, which is similar to the work that's being done here. This is a study by Brown et al., where they were using transcranial Doppler to measure cerebral blood flow and using that to determine a MAP threshold that they would use as their floor for patients that were undergoing cardiopulmonary bypass. And they actually found that when they compared the patients who used an autoregulation targeted blood pressure threshold, there was actually a lower incidence of postoperative delirium. So this is kind of a glimpse at what it is that we could possibly do with these sorts of tools. But when we're looking at this newer framework, that we could run into some stumbling blocks, perhaps. One of the big ones is that surrogates of cerebral blood flow are often used due to feasibility instead of actually measuring cerebral blood flow. In the previous study that I showed you, they mentioned in their paper that it was time-consuming and technically difficult to do the transcranial Doppler, and that it was something that required extra training and extra information. Another consideration is that any measurement that we gather is, of course, just a particular snapshot in time. And how many snapshots you gather and then use in your data generates more data. And so if you are using a lot of different data points and a lot of different moments in time, you end up generating huge mountains of data that you then need to use for your calculations. And a lot of the more traditional calculation methods that we've used for statistical analysis in the past has that we collect data, we gather information, and then we go to a second location and basically take the time to do all this calculation, but that will provide data well after the clinical encounter in question happened. So we are working with a TCD robot that we recently got from Neurosignal, and it uses AI to acquire the optimal cerebral artery waveform. And it's the picture on the right shows the two probes that sit in this headrest cradle that you put little dots to give the robot a pathway between which to drive, and it drives around and it uses AI to find the optimal window and get the best signal available. And then it calculates for you, based on the waveform that it's finding, the cerebral blood flow. So every single beat, you're getting a calculation of cerebral blood flow for each of your cerebral arteries that it's following. And so the artificial intelligence in this case would be using for locating and maintaining the best MCA waveform. It calculates the cerebral blood flow with every beat. And if the patient moves or adjusts, it actually uses AI to refine that same waveform again. It can do it very quickly. Every data point is captured and recorded. And then there's a capacity to integrate with other forms of monitoring, which allows correlation with simultaneous blood pressure measurements and makes it possible to do calculations. And so machine learning and kind of big data, there is enormous amounts of data generated for this. If you're thinking about getting every single heartbeat data point on both your mean arterial pressure and your cerebral blood flow, that's an enormous amount of data if you did it for just an hour. And so then we also can use machine learning to help it figure out when there's outliers, like if there's a blood draw and the arterial blood pressure goes through the roof, or the patient moves, and so there's a period when we don't have a good waveform and there may be a number generated, but it's very discordant with the other things that we're doing. Also waveform data analysis to get the blood flow. We can integrate all of these things and hopefully get to the point where we can derive these cerebral autoregulatory curves. And the endpoint that we're really hoping for is, will this allow us to determine optimal blood pressure ranges on a personalized per person occurrence? So kind of the big questions that we are hoping to answer with this project is it possible to use this method, and is it to determine optimal blood pressure person to person? Is it feasible to build in real time autoregulatory curves to guide in the moment to moment adjustments of blood pressure management? Another thing that we're hoping to look at is, are there conditions that will adjust the autoregulatory curve such that we would want to rebuild a new curve in order to have not just individual person blood pressure management goals, but also individual person, individual situation blood pressure management. The ultimate question from that is, if we are able to personalize blood pressure in a feasible way, is there a clinical difference? And if there's a clinical difference in the short term, the even longer term question is, are there long-term outcome differences? If we're able to do this for patients when they're undergoing anesthesia or when they're in the ICU, can we actually see an appreciable difference down the stream? So that's our project that is in the process of happening, and some of the things that we are hoping to determine. With that, I will turn it back over to Dr. Barker.
Let's see. Okay. So our next speaker is Dr. Matthew Zapf. Here we go. Dr. Matthew Zapf is an anesthesiologist and assistant professor in anesthesiology and research informatics at the Vanderbilt University Medical Center. His research primarily focuses on developing machine learning tools for clinical use in the perioperative setting. As part of his current T32 grant, he has worked on predicting intraoperative transfusion from perioperative variables to guide type and screen ordering.
All right. Thank you, Dr. Barker. Today I'll be talking about some practical considerations for implementing artificial intelligence or machine learning in the perioperative setting. I have no relevant financial disclosures. So in this talk, I'll discuss how we developed an algorithm to predict intraoperative transfusion to guide type and screen ordering at Vanderbilt. And specifically, we'll cover the algorithm development and how we built a pipeline to achieve real-time predictions incorporated into the electronic health record. And finally, how we will use our tool in the clinical setting. In terms of building a framework for this entire process, there's certainly not just one recipe for success. However, I wanted to share some of the things I found important in our experience. So if you have some individuals with expertise in process mapping and strategy available, they can be very helpful in figuring out how a clinical decision support tool, for example, fits into a clinical workflow to maximize the impact on patient care. Engaging leadership is very important. Whenever you're trying to do something new, inevitably it seems that there are unforeseen roadblocks, and it can be vital to have institutional support to overcome those obstacles. In addition, in the perioperative space with so many stakeholders, early multidisciplinary engagement is vital to affect change. And lastly, engaging with health IT is very important in terms of launching your algorithm. They understand how your process could potentially interact with current electronic health record processes. It's really their area of expertise. So in our study, we chose to predict intraoperative transfusion of packed red blood cells to guide preoperative type and screen ordering. So we included the main operating room areas where patients had more complex surgeries and where transfusion was more common, and we excluded ambulatory sites, emergency surgeries where type and screens are uniformly ordered, those that refuse blood products, pediatric patients, and organ donation surgeries. One important first step is determining where the data will come from that will feed into the algorithm so that you can use it in real time. Under the hood of the electronic health records, data must remain strictly organized in order to maintain consistency. And there are several types of uniform data standards that are used to facilitate the exchange of health information within and between institutions. We decided to focus on the information that is stored in the electronic health record when a surgery is scheduled. In this context, an HL7 message is sent in the electronic health record. On the right of the screen is an example of part of one of those HL7 messages. And highlighted in yellow are the surgical procedure code and the surgeon, which were two of the variables that we included in our algorithm. So by using uniform data standards, we can ensure that this work will remain consistent over time and that it's more easily replicated at other institutions. In our modeling efforts, we use Data Lakehouse. That's a large relational database that captures fields from our electronic health record. And while this type of data storage is helpful, it's not necessary to make a model. What is important is that the data that you use mirrors the data source you plan on referencing during the active use of the model, and that it's captured at the same time when you want to use it in the model. So I'll spare you the details of actual modeling. It's something I'm very passionate about, and I'm happy to discuss specifics, at a later time. But I did want to provide some high-level information. So most algorithms are free to use in open source format. One commonly available suite of applications is called scikit-learn. I would say that Python coding is the language most people use for developing AI applications, although there are more user-friendly AI tools becoming available. However, I would caution you against using these tools if you don't have a background in understanding the concepts underlying AI and, especially the limitations. Personally, I've found Andrew Ng to be an excellent teacher. He's the founder of the Google Brain project, and a number of his lectures from Stanford are available online. Briefly, a little bit about how you evaluate a predictive model. This graph depicts 3 of the different models we kind of looked at. For our purposes, we want to ensure a high degree of sensitivity, which means we rarely miss type-in screens for patients who undergo transfusion in the ORs. Another interesting way to look at the results for your algorithm is to look at a reliability diagram. So with a binary classification algorithm, you end up with a number of individual predictions that range somewhere between 0 and 100% probability. So on the left side of the screen is the distribution of the predictions from our data set. You can see most of them are closer to 0% risk of transfusion, which makes sense considering that only 5% of the cases were transfused. On the right of the screen is the reliability diagram. So here, those patients with a similar probability of transfusion are grouped together on the x-axis, and then their real transfusion rate is shown on the y-axis. So if there's a 1-to-1 ratio, that means that the probabilities are reliable estimations of the actual risk of transfusion. When we were initiating development, we created a process map that would explain how our algorithm would work within the clinical workflow. So as previously discussed, when the surgery is scheduled, there's a specific message sent within our electronic health record. So at that time, we check to see if there's a recent hemoglobin available. If there is, we package that result along with our other 2 predictors, and we send it as a payload to an API, which is where our model is housed. It then creates a prediction and routes it back into our electronic health record. However, if there's no hemoglobin available, it will still send that information, and we use the median hemoglobin at that point. But if a new hemoglobin becomes available, we essentially create a new prediction with that new hemoglobin and update the prediction within our electronic health record. So I like this image to explain kind of where an API fits into things and what an API is. So the client in this case is our electronic health record. The request is that payload of information, the predictors that are then sent to the API, which is where our model is housed. It then sends back the prediction as a response to our electronic health record. So these are the flow sheet rows where the image or where the information from our API is stored. So you can see our various predictors, hemoglobin, surgeon, procedure code. We have the binary prediction if transfusion is going to occur, a yes or no, along with the actual predicted probability. So with that information, we can start developing a prototype within our electronic health record. One of our initial prototypes was in our preoperative anesthesia context. So this is the first thing that pops up when you open a patient's chart. We can see with this example, the patient has about a 5% risk of transfusion and would thereby require a type and screen. We also want to display the variables that went into the prediction so that the user can determine how relevant this prediction is for their particular case. And lastly, we started our design for when we want to use our model to discourage unnecessary type and screens. Here we'll use a nudge in the preoperative order set. So when a patient has a very low risk of transfusion, we will auto-select not to obtain a type and screen and then provide that rationale for why. However, importantly, the clinician will be encouraged to use their clinical judgment to make the ultimate decision. So with that, thank you to IARS, to my mentors, Robert Freundlich and Jonathan Wanderer, and to the NIH for funding.
Great, thank you very much. I think we have some time left over, that's everybody, for some questions if we like, or I know we're going to move to a different venue for questions. How do you think we should proceed with that? I fielded some questions in the Q&A box as people were kind of talking. So it's a good time. Is there an easy location to find the next venue for discussion?
Yeah, I will put it in the chat in just a second.
A question in the chat. What are some examples of use of AI in the ambulatory surgical centers? What about AI in, oh, go ahead.
Oh yeah, I'm happy to answer. Some examples I've seen of AI in ambulatory surgical centers are one to predict PACU length of stay, to determine the ordering of case scheduling. So for those that may have a longer length of stay than expected, perhaps you'd want to put them in the beginning or middle of the day so that you don't have staff having to stay super late into the evening and dig into overtime. So that was one example. Another example I've seen is just what type of patients probably aren't appropriate for an ambulatory surgical center, whether that's, they are more likely to have an unexpected hospital admission, potentially require transfusion, things of that nature. So those are some examples I've seen.
I've definitely heard of examples in scheduling and sort of process related implementation. There's another question for you, most likely. I'm particularly interested in implementation and like the idea of a nudge. Any specific examples or resources you would point to for a good example of implementation into an EHR that doesn't get ignored, forgotten, and clicked over?
Yeah, that's a great question. I feel like a lot of us have encountered certain hard stops within the EHR that can become sources of frustration at times because you end up having to click through them over and over. So I think it's just kind of marrying the right process with the right type of nudge or hard stop or whatever it is, while at the same time respecting the clinician and their time and their patients as well. So I don't know if I have a perfect answer to that outside of just being thoughtful about what the end user experience is.
Yeah, I think nudges can be challenging. I think we get alarm fatigue and alarms everywhere and banners on things, and you just stop looking at them for after a while. So they have to. It's hard to figure out what's meaningful in that. Another question: how do we proceed with developing programs for educating colleagues on how to use and integrate AI? I don't know if Ryan Melvin wants to take a stab at that one.
Sure. I think my short answer would be to make 2 book recommendations, and I can also type the titles in the chat. But one book recommendation is a book called You Look Like a Thing and I Love You by Janelle Shane. It is about the kinds of errors that AIs make, and by explaining why they make the errors, the book teaches you what they're doing behind the scenes in like a story-driven way. Again, I'll type those in just a second. And then the second book I would recommend is Data Science for Business by, I think it's Fawcett and Provost. You have to be comfortable with algebra, but they explain how a wide swath of AI and machine learning algorithms work with algebra. And I think seeing behind the scenes what these models are doing and having them demystified sort of is a good place to start with educating folks on how to use them.
Yeah. Let's see. Can AI look at preoperative histories and summarize risk? I don't really know how to answer that. I think we have some headway in the natural language processing, machine learning algorithms to read medical records. And I think you could probably work on algorithms to summarize risk, perhaps. I don't know of any that have done that just yet.
Yeah, we're working a little bit on using NLP to create basically patient histories, which can then be used to ensure that the patient is basically getting the correct preoperative workup. At our institution, we kind of have different levels of preoperative workup. Either they show up on the day of surgery, get a phone call, or go to a clinic that's run by nurse practitioners that have a very formulaic approach to preoperative workup, or to go to a preoperative anesthesia clinic run by an anesthesiologist, kind of being the highest level of preoperative evaluation. So we're trying to figure out if we can kind of automatically allocate patients to the correct pathway.
Similarly, we had the director of our pre-anesthesia clinic recently asked me about could we use generative AI in particular to read past patient notes and surface things that are important for the pre-anesthetic evaluation, deciding ASA status. It looks like I can't send a chat message to everyone, but I sent the book titles to the hosts. If maybe you could send the message to everyone.
Oh, in the chat form.
Awesome, thank you.
It looks like we're out of time. And so glad to continue this conversation in the Doc Matter forum. Does that sound reasonable?
Sure.
Very good. Well, thank you everyone for speaking. Thank you for everyone for attending, and this is a very interesting topic. So much appreciated everyone's expertise.
Thank you.
Thank you.
Thank you.
Thank you.